Hey everyone, so this is going to be a fairly short video, mainly because there's really not a whole lot to go over with gravitational forces. But this is going to be the next thing that we talk about. So far we've talked about how to deal with objects on an inclined plane, objects that are being affected by a spring, and objects moving around in a circle. So another one that we're going to talk about is the gravitational force. Now, some of you might be thinking that we've already been dealing with this. That's what the weight is when we do that RFPDs in Newton's laws. The gravitational force always goes down, Fg equals mg. What else can we talk about? We're actually going to take it one step further and actually talk about the gravitational force between objects that are very massive. So we're going to actually talk about the gravitational force both at the very large scale and at the very small scale. Now, we have a more general equation for the gravitational force. It's given by this equation, Fg equals g m1 m2 over r squared. The equation we have is more of an approximation. It's good enough when we're close to the surface of the Earth or we know what the acceleration due to gravity is at that exact place. We can use Fg equals mg in that case. But if we're talking about something more general, like maybe what is the force between the Earth and the Moon, or if we went onto a planet, what would the force of gravity be there? A place where we don't know the acceleration due to gravity through experimentation. So this is good as a more general equation. I tend to call this the big G equation, as the equation implies there is a giant G in here versus Fg equals mg, which has a much smaller G. You could also think of it as being one of our bigger equations versus the other one. Uh, Everything is pretty straightforward. You should all know that Fg is referring to the gravitational force that's measured in newtons. Now, big G is a new term. It stands for the universal gravitational constant. Now, this number, because it's a constant, is on your reference table. It's on the front page at the very top. It has this crazy unit, which is Newton meter squared per kilogram squared. The nice thing is you don't have to memorize this because it's on the reference table. One of the mistakes that I see though is that people tend to drop it. Don't do it. It's there for a reason. M1 and M2, really straightforward. Those are the mass of the two objects that we're dealing with. Both of them are still going to be in kilograms. So M1 could be the mass of the Earth, M2 could be the mass of the Moon. Now you should know from algebra that because these two things are being multiplied, it doesn't matter which one's which. If M1 is the Earth and M2 is the Moon, you get the same number if this was the Moon and M2 was the Earth. Because 2 times 3 is 6, but 3 times 2 is also 6. And then R stands for the distance between centers. Now, this one I want to make sure I stress. One of the mistakes that I see is that people mistakenly think that this stands for radius. So in the question, they're either looking for the word radius, and sometimes they do throw in what the actual radius of the planet is as a curveball, or they'll look on the reference table on that front page and look for the radius of the Earth or radius of the Moon. R does not stand for radius. If you look on the back page, R stands for radius in some cases, like in the centripetal force equation, or in this case, it stands for distance between centers. So we're looking at the actual distance that the two objects are. One really nice thing that you can think about so that maybe it might not confuse you as much is if you remember when you have the Earth, that's my amazing drawing of the Earth, and the moon is orbiting in roughly a circle, the radius being equal to that distance between centers. Now, it doesn't actually have to be the radius because, again, like I said, sometimes the orbit that it takes isn't actually a circle, but you can kind of think of it like this, that the distance between centers in this class at least will kind of be equivalent to the radius of the orbital path. But you want to kind of remember this word only because they say it anytime they're doing a word problem. They'll say, oh, the distance between centers is blank. So you want to recognize that word. Some very quick comments I want to make. Unlike some of the other equations that we've done where the numbers given in scientific notation were, occurred sometimes, here it's going to be constant. You're guaranteed to have to use the scientific notation at least once, mainly because the big G is always in scientific, but usually because we're dealing with either something very, very large or very, very small, like something on the proton electron scale or at the Earth, Moon, Sun scale. So it's going to be very important that you make sure you plug the numbers into the calculator properly. Now, I showed you in the beginning of the year that if you plug in a number that's written in scientific notation and you don't take these special precautions when you're dividing with scientific notation, you're going to end up getting the wrong number. So you want to make sure that you either put brackets around all your scientific notation numbers, you use the EE function with any scientific notation number, or you set your calculator to the fraction mode and you input it as a fraction so that it looks exactly as you see it on your paper. So again, just be careful when you're using the numbers in scientific notation. Don't forget to square the R term. Again, it says it in the equation, but it's super common that people tend to drop their squares. Don't do it. Just double check before you move on that you've squared everything that needs to be squared. In fact, one of the common things that I'm going to say is if you come up and say, hey, I don't know why I got this question wrong, one of the things I'm actually going to look for is right away, is the answer without squaring the R term? And I'm probably going to say that multiple times. You forgot to square R. You forgot to square R. Again, it comes up repeatedly. Another thing, don't confuse big G and little g. Some of you have a writing style where you either always capitalize your letters or you always undercase your letters, or sometimes you just think that any G is equivalent. Big G and little g are two completely different numbers. Little g for Earth is 9.8. Big G for the universe is 6.67 times 10 to the negative 11th. Two completely different numbers. And like I said, always pay attention. A lot of times they'll give you a question where they don't explicitly give you all the numbers. Usually that means they want you looking at the front reference table for those extra pieces. All right, so here's pretty much the only calculation question. Pause the video work itself, and we'll go over in a second. All right, so here they ask what's the gravitational force between the Earth and the Moon. They don't tell us any numbers in the question, so I have to go on the reference table and use the fact that they're talking about Earth and Moon and what I know about gravitational force to get the information. So I need to know the mass of the two objects, and I need to know the distance between the Earth and the Moon. So all that information is on the reference table. So plugging into my equation, g m1 m2 over r squared, I end up having this gigantic thing. And yes, this is going to come up a lot. This is actually very commonly written. Like I said, a lot of scientific notation can be really tricky plugging into the equation, into the calculator. Very common that you might make a mistake with a unit, so always double check. When you plug this all in, you end up getting that the gravitational force is 2 times 10 to the 20th newtons. The next question says, well, what about the force of the moon on the Earth? This was for the Earth on the moon. Well, as I said before, if you just switch these two masses, if I just switch the Earth's mass with the moon's mass, it doesn't change anything. So my answer will still be 2 times 10 to the 20th. You could also remember that this is a Newton's third law question, that if the Earth exerts a force on the moon exerts the exact same force on the Earth. For every action, there's an equal and opposite reaction. We're not going to actually do any more plug and chug questions because as far as the plug and chug goes, that's it. It's just practice using this equation. So we'll end up doing some more practice questions later on where you'll use this equation, but I'm not really going to go over any more because it doesn't really get more difficult than this. Again, they give you all the numbers. You just need to plug them into the calculator. It is a really standard plug and chug one. There is another few aspects with gravitational force that we're going to talk about. One of them I'm going to save for another video. Now, one thing that I want to point out is that if you're talking about the force between planets, um, the size of the planet actually doesn't affect its gravity. So the gravitational force between the moon and the Earth we found was about 2 times 10 to the 20th. If we actually took these two objects, the moon and the Earth, and we actually condensed them into a small sphere, much smaller than themselves, but kept made sure that they kept their mass, they would still feel the exact same force. In fact, if we took the sun and made it into a black hole of the same mass, our planets, the planets in our solar system, would act exactly the same way. Obviously, we wouldn't be able to survive due to the lack of heat. We would pretty much be annihilated within seconds, but the Earth would still rotate around the sun the exact same way because gravitationally, all that matters is the mass and the distance between centers. It's not about the distance between their surfaces. Now, the size of the planet actually would affect the gravity that we would feel on that surface. So, for example, Jupiter has a significantly larger mass, but due to its also much larger size, it only ends up having about 10 times the gravity of Earth, even though I think its mass is closer to like 100 times that of the Earth. So, mass does play a part in the gravity that we would feel on the surface. But if we're talking about between two objects far away, it doesn't actually play that much of a factor. The other thing, this is actually what I just said before about the fact that this is Newton's third law, that the force that one exerts on the other is the same, vice versa. Moon on the Earth, same as moon as the Earth on the Moon. Moon on the Sun, same as Sun on the Moon or Earth. So here's the next question. Pause the video, works up, and we'll go over a second. Again, Newton's third law. If the force between A and B is 2 newtons, then the force of B on A is 2 newtons. Crazy. That's pretty much the last of the practice questions. There's one last thing that I want to talk about, which is what's called a gravitational field. This is just a question that you have to be able to recognize. So it's a very basic multiple choice question. They say, hey, what does the gravitational field look like? And you just got to pick it. So I'm going to breeze through this quickly. The gravitational field, as its name kind of implies, it's an area of effect essentially around where gravity exists. So if you are in a gravitational field, you are experiencing gravity. One of the interesting things is that according to the equation g m1 m2 over r squared, it there is no value that r could ever be so that the force goes to zero. You would have to go infinitely far away to get close to zero. What that means is that we technically are feeling the forces of gravity on every single piece of matter in the universe. Anywhere from within our solar system. So we're feeling the gravitational force from Pluto. We're feeling the gravitational force from Alpha Centauri. We're feeling the force due to gravity from planets within the Andromeda galaxy and at far end of the local cluster and on the other side of the entire universe. We are technically going to feel that gravitational force. That force may be so small that we would never notice it or be able to measure it, but we do technically still feel it. So the gravitational field is the area where we would feel gravity. The way we actually figure this out, what we're going to end up doing is drawing lines to represent the gravitational field. Um, Now we do this, there's a few rules that we have to keep in mind. First is that the field lines never cross. All right, so you can never have lines crisscrossing. If you see a multiple choice question where lines are crossing, that's immediately thrown out. Another one is that the field lines are always attractive. Remember, gravity attracts objects. We are attracted to the Earth. We're attracted to the moon. We don't get repelled because of gravity. So the lines are always going to go towards whatever massive object we have. And then the last thing is that the denser or the closer the lines, the stronger the field. You can almost think of this as being kind of like contour lines, where the closer the lines were, the steeper the slope. It's similar to that. So the way we figure out the gravitational field, at least at this level, is we'd ask ourselves, if I'm standing on the moon, or sorry, on the Earth, and I'm right here, what direction would the force be? Well, I'd be attracted to the Earth, so I go to the left, towards Earth. If I was over here, I'd be attracted to the right, towards Earth. Over here, I'd be towards Earth, towards Earth. So the arrows would go inwards, towards the Earth, from all different directions. To go over this line a little bit more, as we know, because of the equation g m1 m2 over r squared, the further away the objects are, the lower that number. As r gets bigger, the force gets smaller. So out here, I should feel a weaker force. So the field should be smaller. If we look at the lines, even though my drawing's really poor, you can see that the distance between this line and this line is much longer than between over here and here. So back here, the field is weaker, so the force would be weaker. And that's pretty much it. You just need to be able to recognize this. Technically, there is one other thing, is that the equation Fg equals mg. This is also called the gravitational field strength. Again, if you look on the back of the reference table, it says it. So if they ever ask it, that's what G is. So this is what the field lines look like around the Earth, and pretty much any massive object like the sun or the moon. If we actually zoom in at the surface of the Earth, the lines would look more like this, which makes sense because no matter where you are, the force due to gravity on you would be the same. So the lines should end up being very parallel because the force is the same if we're near the surface of the Earth. And that's pretty much it. So, like I said, it's a plug and chuck type of equation. There is a little bit of an aspect with a graph, which we'll go over later. But again, it's just you should be able to recognize it. You should be able to recognize these gravitational field questions. Uh, Again, it's either you do or you don't know them. And then there's one last thing that I need to talk about. So that's pretty much it for this. If you have any questions, please let me know. Otherwise, I'll see you later. Good luck and have a great day.